All right, let's take a look at properties of radicals. Some of these are going to look familiar just because we introed them yesterday. Some of them, too, we've seen in previous chapters. There are a few things that we have to be careful of here, and I'll go through that and make sure that you feel comfortable with it. This template did get, this shouldn't all be white. This Google Slides template got all messed up, so sorry that the formatting is kind of goofy, but you'll get the information that you need either way. Our goal for today is to be able to simplify square roots, and we're going to throw some cube roots in there. We've already done this, again, a little bit, but we're going to throw a few wrenches in to make it more interesting. First thing, it's important to know when something is in simplest form. Here are the three things that make something in simplest form. First thing, the radicand, or the radical, the square root symbol, or the cube root symbol. That would be the radicand. The radicand, there are no perfect squares or perfect cubes left underneath the radicand. That's going to be a big piece of simplifying today. No more perfect squares left underneath. There can't be any fractions. And then we are not allowed to leave an answer that has a square root or has a cube root in the denominator. Now, there's one question on your homework that's on the back page that you will leave the square root in the denominator, because I haven't showed you how to simplify it yet. So sorry about that, I put one bad one in there, but you'll have one answer with a square root on the back page of your homework today. The big thing that will make it so we can simplify square roots, the main focus, is being able to do this right here. Let's say that they give us the square root of 45. Well, it doesn't seem like we could simplify it. It's not a perfect square. The closest perfect squares we have are 7, which gives us 49, and 6, which gives us 36. But if we break 45 down, like they do there, into 9 times 5, which is 45, I am allowed to split this into 2 separate square roots and take the square root of 9. 9 is a perfect square. The square root of 9 is 3, and 5 I cannot break down anymore. In a similar way, if we have a fraction underneath a square root, we can give the square root to both the top and the bottom, and then simplify whatever we can. We couldn't simplify 3, so we just left it as root 3. We were allowed to simplify root 4 into just 2. So in letter A, they're going to give us a problem where we need to simplify the square root. We need to break it down into 2 numbers that we can multiply, where one of those numbers is a perfect square. So I need to start figuring out what, I could find any perfect square, but I want to find the largest perfect square that goes into 108. So I'm going to start with 108 divided by 4. Okay, that worked out. Let's see if there's a bigger perfect square. Like if 4 goes into it, maybe 16 will also. No, 16 doesn't. So let's try one more. Let's just try 9 because it's in between. Okay, 9 does. So let's go with that. 9 is the perfect square I'm using. 9 times 12 gives me 108. So now I can break it down a little bit further. The square root of 9 times the square root of 12, that would give me 3 root 12. I always have to look back at my fraction, at my square root and see if I can simplify it further. I've got to think, are there any perfect squares that go into 12? Well, yeah, 12 times 4. So I can actually break this down even further. The square root of 4 is 2. Times 3. 3 times 2 is 6. So notice I took a shortcut here. I didn't write this middle step. I just said, oh, I know the square root of 4 is 2, and I would be okay with that. Look at letter B. One thing that's extremely important to keep in mind before we look at letter B is that just like addition and subtraction are inverses, square rooting and something to the second power are inverses. So when we do letter B, we can first break this up into root 9 times x to the third. Square root of 9 is 3. Now, because square roots and something to the second power, something squared, are opposites, I want to break this x down into as many pieces of x squared as I can. If I have x to the third, I can break it down to x squared times x. Remember, this is x to the 1. If we were to go back, we add those exponents together. So now I have 3. The square root of x squared is just x. I can't do anything else with this x to the first power, so this would be my final answer. Let's look at another one like that, letter B. Square root of 25 times the square root of x to the 5th. Square root of 25 is 5. X to the 5th I want to break down into as many x squareds as I can. Since these are all being multiplied, it's the same thing as saying x to the 5th, just in a spread out way. The square root of x squared is x. The square root of x squared is x. And I can't do anything with this. It has to be left under the square root. I have 2 x's out here, so that would give me 5 x squared times the square root of x. A little bit tricky. Let's look at 2 with fractions. Now here with fractions, we give the square root to both the top and the bottom, and then we simplify what we can. 64 is a perfect square. That would give me 8. Numbers that go into 15 would be 1 and 15. Well, neither of those are perfect squares, and 3 and 5. Neither of those are perfect squares. So I'd have to leave my answer as the square root of 15 over 8. Break this down, 81 over root x squared. Square root of 81 is 9. The square root and the squared undo each other, so that would leave me at 9 over x. Last thing, you're going to have the same type of thing with something that is cubed. So if we were to do letter B, you have the cube root of 125 x to the 7th. Well, the cube root of 125 times the cube root, we can break this up into x to the 3rd. Just like something square, the square root of something and something squared undo each other, the cube root and something to the 3rd undo each other. So I want as many thirds in here as I can. 3 plus 3 plus 1 would give me that 7 back in the exponent. The cube root of 125 is 5. These undo each other, it gives me just an x. These undo each other, it gives me an x, and I'd be left with the cube root of x. 5x times x is x squared, and the cube root of x. Last one, let's look at letter D. First, we give the cube root to both the numerator and to the denominator. Now I can take the cube root of 8 times the cube root x to the 4th. I can have an x to the 3rd and just an x. The cube root of 27 times the cube root of y to the 3rd. Cube root of 8 is just 2. Oh, I forgot my cube. Cube. Cube root of 8 is just 2. The cube root of x to the 3rd is just x, and then I'd have the cube root of this single x left over. Cube root of 27 is 3. Cube root of y to the 3rd is y. So here would be my final answer. I know those are just some quick examples. With the rest of the time today, you're going to work on 9.1a extra practice, and you'll get that from Miss Jen. I know that wasn't a ton of examples. I know it's a little bit tricky, but the biggest thing that you need to be able to do is if you have some number, we had 45 in an early example, square root of 45. We need to try to break it down into a perfect square times another number so we can simplify that perfect square. That's the biggest thing that we went over in the beginning. The biggest thing we can get from this. If you look at taking any number that you're given and you try to break it down into something that we can get out of the square, get out of the cube, then you're going to be in good shape.